to the last morning session. First lecture is by Tal Binyamin from Weizmann. We'll talk about sharp or minimality.
Okay, thanks very much. Welcome to this final day of the conference. So I'll talk about sharp or minimality, and this will be kind of a survey talk. I won't talk about really new stuff, so apologies to those of you who may have heard some versions of this talk. Okay, so I'll talk about sharp or minimality. Let me know if the pen goes weak. And I'll start by just briefly recalling the Pila-Wilke theorem that we've heard much about, so just to set up the notation. So I work with a set X of real numbers. And then we had this notation in Tom's talk and in Philip's talk, where we take the rational point height h in x, and this is by definition the points x in x, such that the height of x is bounded by h. How do you like this pen? Is it visible? It feels a bit weak to me. It's okay?
Excuse me?
Oh, sorry, yeah. In x intersect q together. And now I'll also define another piece of notation that we didn't have before, where instead of q, I'll take the points of a given degree g. Okay, so x gh, this will be the set of points x in x. Now I don't need to intersect with q, such that the field that they generate over q has degree bounded by g, and the height is bounded by h. Okay, so by this I mean the field generated by all the coordinates of the point. And well, this height you can take to be the multiplicative A height, or I mean, there are various ways to define the height once you talk about algebraic numbers, but they would all be equivalent for my purposes. So if you're not familiar, you can think about, you just take a minimal polynomial of the point and you take the sum of all the coefficients, or the maximum of all the coefficients, or something like that. Okay, and then the theorem that we saw by Pila-Wilke is as follows. So if we take x definable in an O minima structure and epsilon greater than 0, then the number of points in the transcendental part of x, QH, is less than or equal to some constant depending on x and on epsilon times h to the epsilon. Okay, and I will not repeat on the board this definition, but basically we define the algebraic part to be the union of all the connected semi-algebraic curves in x, and then this means the complement, so everything outside of the algebraic part. Okay, so this is the theorem, and there's a conjecture due to Wilke that actually appears on the same paper as this theorem, and it was mentioned in Tom's talk. So I'll repeat the conjecture, called the Wilke conjecture. So now instead of taking x definable in any O minima structure, we'll take it in some special structure. So now we take x definable in R sub x. Okay, so this was mentioned in Tom's tutorial, and this basically means that you can define it using the field operations and the exponential function from R to R, and then you allow logical operations like unions, complements, projections, everything. And this is known to be O minimal by a work of Wilke. And then the conjecture says that if you are in this special O minima structure, we have a bound that the number of points in the transcendental part should be less than or equal to some polynomial depending on x in log h. Okay, so this is my asymptotic notation, just means some polynomial unspecified depending on x.
The Q points again?
Yeah, oh, sorry, yeah. So this was x trans QH.
And this is something that's known to be achievable. That is to say, you know that you can do this.
So I'll talk about cases where this conjecture is known.
No, I mean that you can't do better. power
Oh,
of
yeah,
h
you
power.
cannot do better than a power of log h. An example where you get a power would be like, say, the graph of the map x goes to 2 to the x. So that's a transcendental map, and it has a logarithmic number of points up to height h.
Mhm.
So this is kind of clearly, well, up to the degree of the polynomial. Maybe that's the best that you can do, and you can try to optimize which polynomial it is exactly. But this is the conjecture anyway. And I want to make another slight version of this conjecture that wasn't part of Wilkie, but that if you take instead the g point, so the points of degree g of height h, this should be less than or equal to a polynomial in g and log h. Okay, so that's not kind of the part of Wilkie's original formulation, but I mean, if you know how these asymptotics usually work out, you can naturally expect that the dependence on the log height and dependence on degree should be similar. And also in the proofs, they somehow play a similar role. So it's kind of natural to expect that if you can prove this, then you can also prove this. Okay, so I want to motivate this conjecture a little bit, but first I'll just say that the conjecture originally was for Rx, but there's nothing there was no specific reason to choose Rx, other than the fact that it's a very classical O-minima structure that Wilkie is, he knows very well. He proved the O-minimality and many things about it, so he chose this one to make the conjecture. But we could similarly make this type of conjecture for a lot of other structures. However, it's not true for all structures. So, for example, this conjecture, if you were to replace Rx by Rn, the restricted analytic structure that we saw in Tomstock, then it would be false. So it was already mentioned that there are examples where the Pila-Wilkie theorem is basically sharp. You can get analytic functions with as close as you like to h to the epsilon. Definitely you can't get polylog h. So there is some class of structures that presumably contains Rx and doesn't contain Rn, and we would like to somehow say what these structures are, where we can expect this kind of better arithmetic behavior, and okay, that's what this sharp O-minimality is about. Okay, but I'll start with motivation. So why should we care about, I mean, we saw that there...
I mean, this is somehow related to Baker's theorem about forms in algorithms or something? Or?
It is related, yes. So I'll say a little bit about why it's related. There will be one example now which maybe indicates a certain relation. I'm not saying that you can get Baker's theorem from this conjecture. I mean, Baker's theorem is quite a fine type of estimate, but it's the same type of estimate that are involved. I'll say a bit more on that later. So, yes?
Is it also clear that you cannot do better in G?
I think it is clear, yes. If you, let's say you look at the graph of the complex exponential, there will be roots of unity. Right? So it will be, you know, I do e to the 2 pi I t. Then when t is rational, e to the 2 pi I t will be a root of unity, and the degree will be like the denominator. So you will get a polynomial number of roots of unity. So like it will be linear in G. Yeah, good question. Thank you. Other questions? Okay, so a little bit of motivation. Why should, I mean, the conjecture originally, it was not motivated, I think, by anything other than the fact that it's a natural improvement that seems to be true in Rx. But it turns out that there are some good reasons to want this. So I'll show two types of motivations. So the first one is for this theorem, Galois orbit lower bound. So this is, I usually attribute it to David and Masser, but I learned in Philip's talk that actually first it was due to Searle.
I think Sarah and Nasser maybe were at the same time.
Well, whatever. This is not the order of the... anyway, but what is the theorem? So the theorem is that we take A to be an abelian variety over Q bar, and P is a torsion point in A. Let's say n torsion, just to fix the notation. Then the theorem says that if you take the Galois conjugates, so the degree of the field of definition of P, I'll do it over Q. It doesn't really matter. You can do it over the field of definition of A, but just to simplify things, this will be greater or equal to C times n to the C for some constant C, depending only on A. Okay, well, of course, the original theorems you can, I mean, this is not a theorem. There's a specific power that you get here. But I mean, this is what we need actually in order to use this theorem in the way that Philip was using it, and this is what I want to prove. Okay, so I will show how to prove this using kind of the Wilkie conjecture, but I will get a certain constant, not necessarily the best constant. Okay, so I will show. Okay. Is
One
this?
would think the opposite, right? One would think that if you had this Wilkie conjecture, you could use weaker Galois orbit bounds, which would make it get much cheaper.
That's also true, but I mean, in this case, it doesn't work out like that. I mean, the improvement from the conjecture doesn't. Well, I mean, you could use lower, like weaker bounds, but actually, in all the cases that we know, we get this polynomial bound, so it doesn't really help us in that regard. But it does help us to get the bound. Is this a good corner of depth? Should I make it bigger? Okay.
Maybe wider than.
Wider? Up to here? More? Good. Okay, so I'll show this proof, and this proof is an idea of Schmidt, Harry Schmidt. Okay, so basically I'll start by, okay, let's set G to be this order of torsion, so, not the order of torsion, sorry, the degree of the field of definition. So basically we want to show that this number G is big. Okay? Now I'll identify exactly as in Philip's talk. I'll identify C to the N. So this is the covering space of my A. A would be C to the N, modulo some period lattice. And I'll identify this with R to the 2N in period coordinates. Okay, so this is period coordinates. 2N, thank you. So we are making this identification in period coordinates, and the point, as we saw in Philip's lecture, is that now the torsion points in A, if you think of them here, they correspond to rational points here. Okay, and the fundamental domain here corresponds to just 0, 1 to the 2n here. Okay, so now I'll consider the map pi from R to the 2n into A. This will be the universal cover. But written in this period coordinates. Now, I mean, formally, this will have some poles if you put a projective model on this, and you can use theta functions as Philip did to get around this, but let me not worry about these details. So I'm saying that this is a definable map because, I'm sorry, so when you restrict it to 0, 1 to the 2n, this will be a definable map, just as in Philip's talk. And I let gamma be the graph of this universal covering map restricted to 0, 1 to the 2n. And this is definable in a no-minima structure. Okay? Maybe in a sharply minima structure, but okay. For now, let's say it's definable in a no-minima structure. And the idea of Schmidt, the new idea was that we will count points on this graph of the cover. So in the previous application that we saw in Philip's talk, we were taking a pre-image of a set and covering only in the universal cover. And then we had to show that there's no algebraic parts there using Ax-Lindemann. Now we are counting on this graph, and then the function transcendence becomes much easier. So, yeah?
I mean, 0, 1 to the 2n is the set you're starting off with, right?
Yeah.
And
So this is basically the fundamental domain when you think of it in
right,
this.
but the a graph needs, and doesn't it need another coordinate, so to speak?
Yeah, I mean, yeah, it's the graph of this, so it would be living in R to the 2n times A, if you like.
Ah, okay.
So this is in
The product.
R to n times A.
Mhm.
Thank you. And, okay, so first of all, the algebraic part of this is empty without any qualifications. So this is just empty. For instance, you can get it from this Ax-Shanwell theorem for a billion varieties, but it's actually a much more elementary result. Yeah. Okay, so now I'm going to fix a point xi in the fundamental domain such that pi of xi equals to I times p. Okay, so what I mean by this I times P is with the group law. Maybe I should write it like this. So there's, our group is an abelian group. There's a group law defined over Q bar. So I'm multiplying P by I. I get another torsion point because any power of a torsion point is a torsion point. And this should be the image of some point in the fundamental domain. Maybe Philip would be very careful and put yeah, P was the torsion point that I started with. So it's the one that I want to it's hidden now. Is it here? Yeah. So I mean, I took some P and I'm trying to show that this G, the degree of the field of definition, is big. Okay, so now what do we know about these points that we've fixed? I want to say that this gives us like pairs of points on the graph, and we know something about their degree and the height. So first of all, if I look at the field of definition of these points, so I take xi and pi, this is all less than or equal to g.
What does that mean, the field of definition of xi?
So xi is just a point in R. In fact, it's a rational point because it's a pre-image of a torsion point in period coordinate.
Oh,
So-
that was my question.
Yeah.
Now it's rational now, so.
Yeah, it's in-
okay.
it's in
Then-
fact
then
rational.
it's
PI
okay,
is
yeah.
IP.
What?
PI is IP.
Yeah. Yeah. So
No,
this
but
is
if it's
xi
ra-
and.
No, stop, if it's rational, then I don't understand.
I mean, in fact, you know, I didn't have to include it here. It's rational. It doesn't change the field of definition. But I'm just saying
But
that.
you really meant QI or you meant pi xi or pi xi?
So pi is pi xi, which I only now added, so maybe it was confusing. But yeah, so I have the points pi where I multiply by I, and then xi is the pre-image. So this gives me a point on the graph, and I'm just taking the field of definition of this point. You're correct that I didn't even need to put xi here because it's rational, but I mean I want to show that the point on the graph has a bounded degree. Okay, well, so here I put a g. You know, maybe if the variety was defined over some field A, maybe I should also put here the degree of the field of definition of A to be safe. But it's not really important. Everything is up to constants depending on A.
I ask myself this question because you don't assume that the abelian variety is defined over Q.
Oh no, I do assume that it's
But
defined over
It
Q.
doesn't matter, it makes it even better, so to speak.
Yeah, I assume it's defined over Q, but yeah, let's assume it's defined over Q. Otherwise, this you would need maybe the field of definition of A here.
The G for the extension is bizarre, but usually G is at the dimension of the
Yeah.
abelian.
Well, you know, there are different traditions. So usually in the counting theorem, this is G, and that's what I'll be counting. What? It's also a group, but I will not be counting group. Okay, so the height of this pair, xi, pi, I'm claiming that this is less than or equal to, well, n. N, you will recall, was this order of torsion. So xi has height n. That's what we used in Philip's law. And then we also need to take into account the height of pi. And now we use some input from their fundamental geometry. These are all torsion points, so they have uniformly bounded height. Okay, so this will be plus some constant, so constant depending on A of 1. So just some asymptotic constant depending only on A. Okay, so this is some non-trivial fact that.
Can you state this? So the theorem is that if I have an abelian variety,
If you have an abelian variety over a number field, then the torsion points have bounded height,
no matter what order.
no matter what order. In fact, there's a canonical height such that the torsion points are exactly the ones with height 0. And then the usual height and the canonical height always differ by some constant uniformly over them. I mean, not over the abelian variety, but once you fix the abelian variety, it's uniform. Okay, so that's some input that we need. And I claim that from these two things, now we will immediately deduce the Galois-Orbit lower bound. So let me show it. Okay, so now we have the number of points on the graph, all of these XIPS, so there's n of them. And this should be less than or equal to the number of points in gamma. I can put a trans here because there's no algebraic part. And then G and this number, n plus OA of 1. And now, if we had the Wilkie conjecture, again, not for this, this is not definable in Rx, but I mean, suppose that these sets were definable in some structure where we have the Wilkie conjecture. So this is this Wilkie conjecture. This would be less than or equal to some polynomial, depending on A, in G and log n. Okay, so now we have an inequality that n is less than a polynomial in G and log n. And then it's a very common trick in transcendental number theory that you can just drop this log n. You can think about it's completely elementary. Whenever you have, if log n is so much smaller, that this will imply that n is less than or equal to some polynomial in A of G.
When you say polynomial, the coefficients are where?
I mean, I just mean there is a certain polynomial with positive coefficients. So it's just asymptotic notation. It's less than a constant times the power of G, or some constant some power. And this is what we wanted. Okay, because that means that well, G should be greater than some fraction of power of n.
So you need the Wilkie conjecture in the G aspect.
You need what?
The Wilkie conjecture in the G aspect.
You need the Wilkie conjecture here in the G aspect, yes. That's a more important aspect for this. But as I said, they are kind of equivalent. Okay, so this is one kind of...
Well, no, I think maybe the point was that you know, and we have epsilon.
Yeah. So here, really, the important thing is that you need a polynomial in G, and in the height, n to the epsilon would be good enough for this application, yes. But again, when you prove it, it's kind of, you get both of them automatically for the same reasons. Okay, so I want to show one other kind of application, which is maybe kind of slightly related to
And this idea also works in the other context, like Andreoff, etc.
So this is indeed the idea that works for Andreoff. I might say a little bit about it in the end if I have time. The difference is that, well, here, I will show later, there is actually a Sharp-Leo minima structure that contains these sets, and you can get it really from the general theory. For Andreoff, unfortunately, we don't have a Sharp-Leo minima structure yet. It does follow from some kind of partial result. I mean, we can get this counting statement, but not the general Wilkie conjecture. So if I have time, I'll mention it in the end. Yeah, but kind of the exciting thing about this proof of Schmidt, it wasn't to reprove the abelian case, which was well known. It was that it kind of gives a general way of deducing Galois orbit lower bounds. And for instance, in Shimura varieties, we were still able to apply this idea, where the previous methods were not available for the most general Shimura varieties. Okay, so I'll show one simple other kind of application.
But you need to know the X channel somehow before, right?
Yeah, although, I mean, this is kind of a very weak kind of function. We're just saying there's nothing algebraic in the graph. So it should be kind of algebraic at the same time, up and down, and also the relation should be algebraic. You can very easily rule it out for monodromy reasons. It's much, much weaker than axial.
Yeah. What is a replacement on a Shimura variety of the statement in use here that the torsion points are uniformly bounded? Is the height of the torsion points?
So there is a statement, a deep statement that was proved with your help, that the height of a CM point in any Shimura variety is bounded by discriminant to the epsilon.
Yeah.
So this
you
was
have
proved.
to go that far to do that.
Yeah, I just mentioned this is a theorem of Pila, Shankar, and Zimmerman with an important contribution by Hélène and Michael Groschenig. And I mean, that was kind of the missing ingredient. So when you have that, you can try to apply this strategy with the Poilot counting and you get a Galois orbit lower bound. Although it actually happened in reverse. So we first proved the implication and then they proved the height bound. But anyway, that's the way it works. Yeah, other questions?
Thank you.
Okay, so I'll show another kind of theorem that indicates some connection maybe to Baker's type of stuff. So I'll let gamma be just the curve y is equal to x to the alpha in R square, where alpha is a real number which is not rational. Okay, so it's a multiplicative group in R2, but it's not an algebraic group. And then the statement is that if you look at the rank of the Q bar points on this is finite. So you look at all the algebraic solutions of such an equation, you get finite rank. You can claim that you get really finiteness because it's a group. As soon as you get one, you can get many, but you get a finite rank. And actually, this rank is less than or equal to 3 by the 6 exponentials theorem. It's a famous result in exponent theorems. Famous result in transcendental number theory. So I'm saying that, well, I mean, what power you get, it would really depend on what version of the Wilkie conjecture you have. but you can get this kind of statement from the Wilkie conjecture, and you can get much more general statements. So I think this is an idea that due to Jonathan Pila. Was there someone first? Yeah, probably Jonathan first. Okay, so I'll show the proof. It's very simple. So okay, suppose we have many points here. So let's take P1 up to Pn to be points in this gamma Q bar. Question? So multiplicatively independent. So I'll take a lot of multiplicative independent points, and I want to show that actually n has to be bounded. Okay, so the idea is we'll just count these points, and we'll count not only them, we'll count all of their products. Okay, so we get a lot of different products using just a group law here. So for k in n, let's look at this set. Sigma k, this will be p1 to the alpha 1 times ... pn to the alpha n, where all the alphas are between 1 and k. Okay, so we can form all of these products, and they're all going to lie on our set gamma, so we have a lot of algebraic points on gamma.
Alphas are integers.
What?
Alphas
Yeah, the alphas are just integers, just the powers.
Alpha n.
Yeah, sorry, alpha 1, alpha n, right. And okay, so now let's look at the points in this set. So what I'm saying is that, well, I have k to the n points in this set, right, because I just do. And so this is less than or equal than the number of points in, okay, well, in fact it's equal. But this is less than or equal to the number of points in this gamma, because they're all in gamma. And then here I should put some constants. So there is, what will be the degree? So all of these points have some joint field of definition G. So let's put some G. It will just be a constant, it doesn't matter. And then what is the height? The height, well, I'm multiplying, so k, I'm multiplying k times for each of these, and I'm doing this t times, so it will be something like 2 to the O of nk. And that would be the multiplicative height. And then, by the Wilkie conjecture, this should be less than or equal to some polynomial, depending on this gamma, in G and nk. Okay, and now let's say this polynomial is some p. Then, when we take n to be bigger than the degree of p, and k much bigger than n, this will give a contradiction. Okay, because this is k to the n, and here we'll get k to some degree smaller than n, and this n will be much smaller, so you can easily see that this will give a contradiction. So of course this isn't Baker's theorem. Baker's theorem is about, you start with an algebraic group, not a transcendental one, and you want to show that if you satisfy some kind of low height condition, then you actually live in an algebraic group of smaller dimension, but kind of the machinery is similar. So in Baker's theorem, you start with a point, you multiply it, you get many points, and then you use some interpolation methods, and that's exactly the same thing that goes on here. Okay, so these are my motivations for.
So you first choose n. This also give you g.
Yeah, I mean g is just a constant because I just fixed some points. So.
Depends on the p switch to it.
So.
Choose after you're choosing n.
I mean p is just it comes from Wilkie. It's independent of n and g and everything. It's just the polynomial in the Wilkie conjecture, and I'll take n bigger than this polynomial, so that this k to the n beats like this k to the something. And then I'll take k much bigger than n, so that this nk doesn't make a difference. It's basically the same as k. Okay? Any questions?
So I'm just remarking that, after choosing n, you choose the points, and this gives you the g value? No?
So I started with points.
This depends on n.
Yeah, so I'm saying, suppose that you have n points. now I'll take, I mean, there is a degree here that doesn't depend on n. So I'm saying, kind of assume towards contradiction that you had such points, P1 up to Pn, where n is very big, bigger than this degree. Because this degree depends on nothing, it's just Wilke's conjecture, and then I would get a contradiction. Clear? I mean, the g is like a constant here, so. Hmm?
Now, my confusion is also concerning the G, that was sort of the degree of the field generated by P1.
I mean, the point is that they have some fixed field, and now I'm increasing k, I'm not changing the field of definition. So I mean, this g is a constant, but when I make k much bigger, it will kind of kill off this g term. But yeah, we can keep going over it maybe later. Okay. So now I want to talk a bit about this. So okay, this was assuming that we have Wilke's conjecture. Now I want to talk about some axiomatic framework that gives us this conjecture. Yeah. Okay, I'll use this one. Okay?
We are
Okay. So
okay, we are okay.
so now I'll talk about this sharp or minimality.
Can I ask something, Carl?
Yeah.
About this latest theorem you have, based on Pila idea?
Mm-hmm.
Is there a more general thing you can show? Like y equals the alpha is very cool, it's very special.
I mean, it was just to make it simple to write, but you could take any multiplicative group, and defined over. So take a multiplicative, an algebraic group, if you like,
Yeah.
and take some analytic subgroup of that,
Oh, sure.
and then look for algebraic points that don't lie in an algebraic subgroup contained in your analytic group.
Sure. I'm just wondering, can you show, say, some sort of, this is kind of like Channel's conjecture is almost true in some specific sense, right? With find too many exceptions kind of theorem. I'm
Mhm.
wondering if you can show a similar thing, where you take a family of numbers you can get from Channel's conjecture and algebraic numbers and show that most of the time, how to say it, percentage degree is almost what it should be, up to like an O of 1 or something.
Well, I mean, it's quite special here that you have the group structure, but I can prove something in the direction of that there are few counterexamples to Channel conjecture, but yeah, we can talk about it. Okay, so now I'll take S to be an O minimal structure, and for me, I'll just identify this with a collection of all definable sets. Okay, so model theorists usually, they include the interpretations of some functional constants and the relational constants. But I just think about a big collection of all the definable sets in the structure, and that would be my structure. Now, a sharply or minimal structure, sharply or minimal, yeah? Sharply or minimal structure on S is, so I want a collection of, collection omega fd subset of S, where fd are integers. Okay, so this is like a collection of subsets, and it actually forms a filtration. Okay, so I want omega fd to be contained in the intersection of omega f plus 1d and omega fd plus 1. So what I'm saying is I'm putting some filtration on all the definable sets. Again, the union over fd of these omega fd's is S. So every set is eventually in this filtration, and they give me a certain notion of some complexity on the sets. Okay, so it's not a well-defined notion. It's not that for every set I can say what is the format and the degree. I can just say what are all the sets of a given format and degree. Okay, usually in semi-algebraic geometry you have just a degree, and then you can talk about the minimal degree, and that would be the degree of a semi-algebraic set. But here, because I need these two indices, then I can only talk about the filtration. So this is kind of unfortunate, but necessary. So I want such a collection. And also I want a sequence of polynomials. A sequence, and you'll see what is the role of this sequence. But I have a sequence of polynomials depending on f. Okay, so this is the data. I have this filtration and I have a sequence of polynomials, and now I'll tell you what the axioms are. Okay, so the axioms are as follows. So, I mean, this data should satisfy certain axioms. So, for instance, suppose that I have A in omega fd and the B in omega fd prime. So I have two sets. Then I want the complement of A to lie in omega fd. I want the projection of A to any kind of fewer coordinates to lie in omega fd. So this is slightly different than so we had several iterations of these axioms, and in fact they are all kind of equivalent, but I mean, so just if you happen to know previous versions of this, I usually had an f+1 here, for instance, but we found out that it's equivalent not to increase it. And I want
Projection of what?
the projection of, sorry, of A. Thank you. So if you project, you don't change the format and degree. And I want the union and the intersection to lie in omega f d plus d prime. So if you take a union or intersection, you are kind of summing the degrees. And I want, finally, R times A and A times R to lie in omega f+1d. Okay, so this notion of format is quite similar to dimension. The only problem is that the projection doesn't draw it. Okay, so if I had here that when you project, you decrease the format, then, I mean, it would kind of follow from this that the format is basically the dimension. But what I'm saying here that when you multiply, you increase the format, and then when you project again, you do not decrease the format. That's why format is not dimension. And we don't know that we can reduce to, I mean, we don't know how to do things in such a way that this will decrease the format when you project.
So it's like a homology factor.
Maybe you can explain to me why later. But it's like,
It's some kind of axioms, yeah.
if you have model completeness where everything is a projection, then it's like the dimension of the thing that you projected, more or less. Not exactly, but more or less. Okay, so this is like, these are analogs of the axioms of maybe just any structure, if you like. You can put this on any logical structure. This is only about the logical operations and how they affect the format and degree.
If I apply any linear transformation, it's does that
Just a moment. So I'll put number 2 here. So the second one is about relation with the field operation. So for example, linear operations you can do not in every structure, but you can do in a structure over a field. So we have a second axiom that says that if you have a polynomial in x1 up to xn, and you look at the hypersurface defined by this polynomial in Rn, this will be in omega n degree of p. Okay, so this is about the interaction between this filtration and the structure of the field. So it says that like on the level of semi-algebraic sets you have the same thing that you normally have. So for instance, the graph of any linear transformation would be, you can write it like a hypersurface or intersection of hypersurfaces, and then from this you can show that, well, perhaps you need to increase the format by a constant. But I'm not sure if it would be really the same format and degree when you make a linear transformation, but it would increase by a constant.
Is it n or n minus 1?
This is n.
So it's not much.
Well, but also in semi-algebraic geometry, the kind of the ambient dimension is it's what goes into this complexity parameter.
So why do you ask that the degree to be additive on the intersections and not?
I mean, it kind of doesn't matter. So if I put a product here, I would get an equivalent notion in the sense that whenever you have this kind of filtration, you can define a new filtration that will have the same thing with a sum. So we are really always thinking about these filtrations up to some kind of equivalence. I'll try to explain a little bit what kind of equivalence later, but I mean, it really kind of doesn't matter. It's like in semi-algebraic geometry, you can define complexity as the sum of the degrees of the equations that define the set. Or you can take a product, but I mean, it's not that sharp like Bezout theorem where you expect to get exact equality. So some.
Everything's gonna be polynomial in degree, and sort of.
I mean, eventually some bounds are polynomial in the degree, depending on the format. So, I'll get to the bounds right now.
Can I ask a stupid question?
Yeah.
It seems that you can write down polynomials with unboundedly many variables in degree with no real solutions, which makes empty set to be in all the pieces of filtration.
Indeed, it's a filtration. It's an increasing filtration. So
And
certainly, the empty set is everywhere.
But then, if you take any set and take union with an empty set, it will also make it to be in any set.
Yeah, because the filtration it's increasing. If a set has some format and degree, it's
it goes to another
automatically
direction.
Yeah, it's an
Yeah,
increasing
yeah.
filtration. Over
Yeah,
there.
good.
Yeah, thank you. Yeah. So the filtrations are always increasing. So this is you can do for any structure over a field actually. It's still not about O minimality. So the final axiom is about O minimality. And the axiom of O minimality says that if you have a subset of the real line, it consists of a finite union of points and intervals. Okay, and then you can kind of imagine what would be the last axiom here. So if I have a subset of the real line, and A is in omega FD, then the number of connected components of A is less than or equal to some these polynomials that I had there, P, F of D. Okay, so we are saying that this general finiteness of O minimality, it tells us that we have a finite number. Now it's actually a polynomial bound in a degree, and which polynomial you take depends on the format. So this could be like d to the f, or d to the 2f, or something much more horrible, probably. I mean, we are not saying anything about how it depends on the format.
But in practice, that's what's realistic, d to the f or things like that?
What's realistic is maybe d to the 2 to the f.
Ah.
That's what you usually get in semi-algebraic geometry. This kind of is connected to cell decomposition and quantifier elimination. So for semi-algebraic geometry, it's usually doubly exponential in the dimension. That's why it's very important to separate here the degree and the dimension. So even in the classical case of semi-algebraic geometry, you get very bad dependence on the dimension, but you always get polynomial dependence on degree. So we are kind of trying to emulate that in a more general
Is your
context.
F ever going to infinity? Or
What?
in practice, is your F ever going to infinity, or are you only ever studying bounded F?
I mean, depends on what you mean, but yeah, let's say if I apply this thing to this proof for abelian varieties, and okay, if you consider abelian varieties of genus G, the format is going to be roughly G.
Okay.
So if you care about every genus, it will go to infinity, but yeah, like in the non-trivial part of the argument, F has to be fixed somehow, because everything is, I'm not specifying how it depends on F, I'm just saying there are some polynomials.
So roughly if some bounded number of parameters that you play with, this will give you a bounded on the F that you need.
It's something like that, yeah. It's something like how many parameters you use to build up the set. Maybe it has something to do with the essential dimension that we saw previously. I don't know. Okay, so there are some examples. So R alg is sharply or minimal. This is kind of this follows from.
Just to get some intuition, so you can always realize 1 and 2, but not 2.
Yeah, I mean, you can always define things that just transitively you close these filtrations under other operations, you'll get some filtration. But the question is, can you then bound the number of components? That's the hard part. So, and this hard part for R alg is done because there are effective cell decomposition results. So I don't know who to attribute this to. It's very classical, but it's I normally say Tom here because the non-trivial part is Tom's lemma. So there is a certain way to do cell decomposition in every O minimal structure, but that doesn't give you sharp O minimality. So if you want to get sharp O minimality, you need a good cell decomposition algorithm, and that is something that Tom invented, or at least it's based on Tom's lemma. So that's the new ingredient that we have only in the semi-algebraic structure.
Can you say what filtration you think in this case?
Well, in this case, you can, okay, let's put it like this. We can take this transitive closure of the, start with just a polynomial with this axiom, and then close these filtrations transitively up to all these operations. And as Bruno said, the only thing that you will need is to show that there are polynomials satisfying this. And to show that there are such polynomials, it follows from effective semi-algebraic geometry results that are known, and basically we go back to Tom.
Why did you call it sharp and not effective or minimal?
because I mean, you could say effective even if it wasn't a polynomial, right? And you wouldn't need two parameters. Like I could have just format and call it effective. But yeah, I mean, sharp is supposed to mean that you, in the degrees, it's really kind of as sharp as we expect. Okay, so RRG is sharp polynomial. Rn is not. So I leave it kind of as an example, but basically you can take an analytic function like you know, z to the an, where an is rapidly increasing, say doubly exponential or something, and you'll easily see that this is a counterexample because it will intersect polynomials with too many points. So this kind of lacunary, or somebody made fun of me and told me it's not lacunary, it's lacunary. So I'm not sure which is correct, but I forgot which one was the correct one. But anyway, with this kind of power series, it cannot be in any sharply minimal structure. So Rn is not sharply minimal. But okay, we need, if this is all we know, then it wouldn't really be interesting. So we do have one example. So it's a theorem with Vorobyov that the structure of restricted Pfaffian structure, so this is restricted Pfaffian, is sharply minimal. Okay, so that means we take these Pfaffian equations that were mentioned a few times before, and we restrict them to compact domains, and we look at the structure that they generate, and this will be sharply minimal. Okay, so this is the theorem with Vorobyov, and well, I mean, I believe that even without this restriction, it should be true, but this is in the works. Okay, so there is at least one example of a sharply minimal structure, but I want to explain why this theorem is kind of not enough, and why I actually never defined, I mean, there is one missing ingredient that is actually the reason why nobody ever defined this sharp minimality. So for that, I want to make one other definition. So let's say sharp cell decomposition. So I'll say that a structure has sharp cell decomposition if whenever you have A1 up to AK, say subsets of Rn, with Aj is in omega Fd for every j. So suppose you have this data, then cell decomposition says that we can find a decomposition of Rn that's compatible with all the cells. That's the cell decomposition theorem that Tom mentioned. Okay, and I want to say that you can actually do it, write a cell decomposition, so a union, disjoint union of cells, and I want to have good bounds on the number of cells and the complexity of the cells. Okay, so I want the number of these C alphas to be less than a polynomial depending on f of d and k. And I want every cell C alpha to have a bounded degree. So in omega, O sub f of 1 and a polynomial depending on f of d. Okay, so this is what I would like to have. I would like to know that whenever you take sets of bounded degree and format, then you can make such a cell decomposition. And this is...
So what is the relation between A and C?
So, I'm sorry, this is compatible with... so this compatible
The AJs are unions of the
with AJs. So that means that each cell is either contained in AJ or disjoint from AJ. So that is what is called a cell decomposition. So I want, thank you for the question. I want this decomposition to be compatible, and I want to know something about the complexity of the decomposition. And you know, O minimality is really defined only in order to get this cell decomposition. That's, as we saw in Tom's talk, you define it, and then you prove cell decomposition, and then you can start working. So if you don't have such a result, then it would be kind of pointless to define this whole theory. So, so you can probably guess what my next statement would
All
be.
these things make sense also of periodic fields? Or?
Well, we think so, although it's quite new and we didn't do it yet. But then the question is, So does every sharp O minimal structure have this sharp cell decomposition? I mean, that's a natural question. Without this, you cannot use this theory. And in fact, this is open. Okay, so that's actually why nobody ever defined this, I would say. I mean, because we don't know how to prove this, and therefore the whole thing seemed pointless. But there is a workaround. So what we can prove, which is really the reason for introducing these abstract foliations and so on. So this was first in my work with Vaubiol. This was specifically for the, this Pfaffian structure, and then also with Novikov and Zak in general, is that, so if you have such a sharply or minimal structure, then there exists another filtration, omega star, which contains omega. So I mean, for every FD, omega FD is contained here.
Again, in 2 parameters.
Yeah, with all the data, such that this S omega star.
All that, I mean, also satisfying all the axioms.
Yeah, so I'm saying now it's this S omega star is also sharply or minimal, so it should satisfy all the axioms, and has this sharp cell decomposition.
You can sort of refine to get a filtration with a sharp cell decomposition.
Yeah, you need to refine it, but I mean, so first you can say, okay, let's do a cell decomposition and put all of these in, put all the new cells into the new filtration. But that's kind of cheating because then you have new sets, you have to do cell decomposition again, and you will keep going, and it's not clear that you will get a filtration in this way. But actually, there is a way to work it out so that it doesn't go in circles, and you can actually build such a filtration with this property. So this is what we didn't know before, and I mean, this is kind of the reason why we didn't just use some fixed notion of format and degree. So we have to really work with this abstract filtration so that we can change the notion to apply these kinds of constructions. Question?
To be clear, the cell decomposition to get for omega star gives you cell decomposition
In omega star. Yeah, I mean this this structure has this property. So if you take something with omega star format and degree, you will get cells with the same omega star format and degree. Okay, so finally, in my last few minutes, I'll just say how this connects to this Wilkie's conjecture. So for that, I'll need one more quick definition. So definition, I'll say that this, if you have a sharp minimal structure, it has sharp derivatives. Sorry for all the sharps. If whenever you take a function f from Rn to R, then for every alpha in n to the n, you can look at the alpha partial derivative. So I mean, I take a partial derivative in the for this multi-index vector, and this guy will lie in omega, and here I will have, let me rewrite it there. So f alpha will lie in omega, and here I'll have some format which depends only on the previous format, and here I'll have a polynomial depending on the format in the degree of the original. Oh, I'm sorry. I want to take
the graph,
The graph of f.
FP.
Yeah. So when I say this, I really mean that. Yeah. So I want to say that the graph of f is in omega fd.
And then the graph of f alpha.
And yeah. So here it's really the graph, but to be formal, belongs to this with d and the absolute value of alpha. So you can get something similar to this for every sharply or minimal structure because the derivatives, you can define them using epsilon delta definition. The problem is that this alpha would go here. Kind of if you want to write out this definition, it will become kind of longer and longer, use more quantifiers as you take higher derivatives. And we want alpha to be here. So this is a property that you can expect when your functions satisfy algebraic differential equations. Okay? Because then when you take derivatives, it's basically a polynomial in the previous functions. So indeed, what we show, some fact or theorem, is that this restricted Pfaffian structure has this property. We don't know in general. I mean, if every sharply minimal structure has this property.
Can you
And the
define what this how tough is, or it's complicated?
so, I mean, it's the structure generated by all the restricted Pfaffian functions. And
What is restricted function?
I mean, restricted just means you take it on a compact domain. And Pfaffian function means that there is this triangular system of differential equations, like I guess Tom talked about and Harry talked about. So f prime should be a polynomial in f and the variables, and f2 should be a polynomial in f2 and f1 and the previous variable, and so on. So for example, this includes exponential functions and abelian functions, but not, let's say, covers of Shimura varieties, as far as we know. Okay, and then the theorem, which is joined with Novikov and Zak, is that, okay, if your structure S omega is sharply or minimal with these sharp derivatives, okay, and X and A is in omega FD, then the number of points in the transcendental part GH is less than or equal to some polynomial, depending on the format, in the degree G and log A. Okay, so it's like a strong form of the Wilkie conjecture. We are saying it's polynomial in G and in H, and it's even also polynomial in the degree of the set itself. And well, in fact, from this theorem plus this theorem, you know that Wilkie's conjecture holds for this restricted Pfaffian structure, and that actually implies that it holds also in Rx, even though Rx is not formally restricted, but there is a reduction based on model completeness. So yeah, I will not have time to show it, but I mean, just trust me that this in particular implies the original Wilkie conjecture. And this is what we would like to use for the Diophantine applications. The only problem is that we don't know yet that, let's say, period maps live in a sharply or minimal structure. So I do have some partial results that basically allow you to prove this for graphs of period maps, in most cases that arise in applications, but I cannot quite get, you know, all of the axioms in full generality. So that is the conjecture that we're working on.
You say restricted Pfaffian, so Rx is included because it's not restricting the structure?
Yeah, Rx is not included, so there's a certain reduction. Because Rx is model complete, you can actually reduce it. It's a few lines based on known theory that you can actually prove the Wilkie conjecture for Rx using this result. The idea is that you can restrict, but you can restrict to any box. It doesn't matter which box you restrict to. So you, I mean, kind of, it doesn't enter the bound, which box. So you do it for large enough boxes, basically. But I mean, there is still some magic that goes into it, so I can explain later for those who are interested. Okay, I'm out of time. I stop here.
Thank you very much. Any more questions?
Yeah, a small question, but I apologize if it's completely out of track.
Don't apologize.
So, because I don't know this Pfaffian structure. So if you take any smooth complex variety,
Yes?
and you take a linear differential equation on it, so there is a notion of a torsor, which is a torsor under the Tanaka group of the linear differential equation. And I mean, that's the basis of Colchin geometry. And I'm asking you whether this is part of your Pfaffian theory here.
I think that they are probably not Pfaffian. I do think that it is sharply or minimal, but that is a kind of a conjecture. I think that whenever you take, for instance, linear differential equations with quasi-unipotent monodromy,
Yes.
then the solutions, if you restrict them, if you make a branch cut, the
Yeah,
solutions
exactly.
live in a sharply or minimal structure, and I have many partial results in this direction. This is exactly what is used in this proof of Galois bounds for Shimura varieties. And I mean, this technique applies to any period map of variations of Hodge structures, or any solutions of linear differential equations with quasi-unipotent monodromy, at least with regular growth. But it's not, so I mean, we know a lot, but we don't know this full axiomatic thing. We cannot prove it unconditional. Yes?
Do you also have results, estimates for the complement or for the images of the finable maps
Yeah, so one of the axioms is that if you have a set of given format in degree, the complement has the same format in degree. So you can, yeah, and that is that is maybe that is part of the hard part. So the reason why people couldn't build it before is exactly that Gabrielov and Vorobyov, they had estimates for the complement, but it wasn't sharp. The format was depending on the degree, so it wasn't of the correct form. That was like the main roadblock to building this sphere.
And also for the image, so for the final set, the final map to look at the image.
Yeah, because I allow projections, and the image you can first build up a product, and then take a projection, and you'll get the image. So it's also kind of basically everything you can write with first order formulas is covered because my axioms are kind of just repeating all the first order formulas.
Okay, let's thank the speaker again.